Morning, students. Today, let us all see the last part of our unit 1, right? So, the last part of unit 1 is our LEX tool. Let me share the screen first. So, let me start the slideshow, right? So, today we will see LEX tool. So, as you all know, I am Jaitambi from CSC Department, RMD Engineering College. Right. Now, LEX. LEX is a computer program that generates the lexical analysis. It is commonly used along with our YA. So the first phase of the compiler is lexical analysis. The second phase of the compiler is our syntax analyzer. So the tool used in our lexical analyzer is LEX tool, and the tool used in our syntax analyzer, otherwise called as parser, is our YAC tool. LEX reads an input stream specifying the lexical analyzer and writes a source code which implements the lexical analyzer in the C programming language. Now, the three basic classification of the representation of our code in our LEX is, first you will be having the definition part. Then you will be having the transition rules. Finally, you will be having the auxiliary functions. Each and every three part will be separated by the percentage symbol, right? So as you all see from this example, first you have the hash include stdio.h, that is a preprocessor, right? And then we have the rules function, and we say that it is 0 to 9 plus, that is, it is for integer, right? So now the LEX2 is going to see, give the output that it saw an integer or not. This is a simple LEX program, right? So it is going to check whether it is having numbers from 0 to 9 plus represents one or more number of times repeated. Okay, let us see the example now, right? So the last part, as I said, it is auxiliary function. So that is our main function. We are calling this LEX2, that is YY LEX function. Now it will go to that given input string and it will find whether it is having any numbers. So how many types of integer it is identifying, those many it will represent. If this input is given to Flex, it will be converted into a C file, lex.yy.c. This can be compiled into an executable which matches an output strings of integers. Now, this is your basic block diagram of our LEX. So you will be having the LEX source program lex.l, right? Then you will be having the LEX compiler, and the output is lex.yy.c. And this will be given as input to the C compiler, and finally you will be having the out object file a.out. Now to this object file, you will be giving the input stream, and it will divide the input stream into the various sequence of tokens. You all know that the sequence of tokens will say whether it is an identifier, letter, special character, keyword, right? A relation operator or logical operator, right? Or it is a function name, or it is what is it? A dot operator or a semicolon, everything it will represent. Now, let us see for the given LEX program in our LEX tool, let us give the input as ABC123, Z dot exclamatory symbol ampersand star 2G J6. Now here you find that 123 is integer. So the program will print, yes, I saw an integer 123. Then next, all are special characters and alphabets. Then it is seeing the integer 2. Then finally it is seeing the integer 6. Now this will be the output given by the LEX2. Now let us see the YAC tool in our parser generator, that is a second phase of the compiler, otherwise called as syntax analyzer. Now let us see what is the expansion of YAC. YAC is yet another compiler. It is a computer program for Unix operating system developed by Stephen C. Johnson. It is a look ahead left to right most derivation. Left, that is, you are going to read from left to right, and the derivation is the rightmost derivation, that it comes under LALR, right? Parser generator, generating a LALR parser based on a formal grammar. The input to YAC is a grammar with snippets of C codes called actions attached to its rules. As we saw in our LEX tool that we had three parts, here also we are having those parts. Its output is a shift reduced parser in C that executes the C snippets associated with each rule as soon as the rule is recognized. Typical actions involve the construction of parse trees. The call node, right? The parameters are label, comma, left, comma, right. It constructs a binary parse tree with a specified label and children. Now the rule will be expr colon expr plus expr. Now how it will be represented in the form of the node. So in our syntax tree, if you want to add two operands, plus will be the operator. and your left child will be the operand 1, that is $1, right child will be the $3. So it is represented as $dollar equal to node. That $dollar is your resultant operand node, the function, right? The parameter is having three, right? The first one is the operator, that is a plus. The second one is the first operand, that is the left child, and the third one is the right operand, that is the right child. Now this is block diagram of our Yak. As we saw in our LEX tool, our Yak tool is also having certain steps while execution. So first you will be having Yak specification translate.y. Okay, the Yak compiler will generate the y.tab.c code. So this code will be given to the C compiler and it will develop the object code. And to this object code, if you give the input, we'll get the output whether the syntax is correct or not. Right, let us see the sample Yak program. So the first one is your declaration part. So you say hash include ctype.h. Right, now the token is the digit. Right, so your first line in the production is line expr. Right, so you are printing that line. Okay, percentage is /n $1. Right, now next one is the addition term. So this is your context-free grammar. So you all remember that context-free grammar is VTPS, where it has a set of non-terminal, terminal, production, and the starting symbol. So the production, as you all know that the production is L tends to E tends to E plus T or T tends to T star F or F, and F tends to expression or digit. Right, now here EXPR plus term. So you are saying you are adding $1 plus $3. Next term 2. You are multiplying $1 into $3. And for the last one is you are just assigning the value. Right. Yak program to implement a calculator and recognize a valid arithmetic expression. Right. So first you are having the stereo.h, then y.tab.h, then your int y/l val is an external variable. Now the rule is you are saying what is a digit. Your digit is 0 to 9. Plus represents it is positive closure one or more number of times. Right. So you have y/l val is equal to a to I of y by text. Then you are returning the respective number. Right. So finally you are saying return 0, the return y by text 0. Right, and then you are invoking the function wrap. Right, then you return 1 true. Now that is your LEX tool code. Now let us see the parser code. Okay, so now you are, as usual, the first part is the definition part. Right, so you invoke that header file, then you are initializing the flag as 0. Then in your lexicon analyzer, the token identified is your number. Right, and the various operators we see here is plus and minus, and these are all left associative. Okay, and we are going to read from left to right also. And then you have multiplication, then division, then modulus function, and then you have the open and close parentheses. Okay, now rule expression. Rule section is over. Now next is our arithmetic expression. Right, so you are going to print the result. Our result is in which operand? $$ operand. Okay, right, then finally return 0. Right, so as you all know that we are having addition, then we have subtraction, multiplication, division, modulus, then open bracket parenthesis where we just assign the value. Okay, now so what is your E plus C? It is $$ is equal to $1 plus $3. Now what is E minus C? Same as above with the operator minus. So as you see the screen, it goes on. Okay, now your driver code is over. Next we will see the main. Now, what is there in our main part? Enter any arithmetic expression which can have operations like addition, subtraction, multiplication, division, modulus, and parentheses. Now, you are invoking the YY pass. If the flag is 0, it means that the entered arithmetic expression is valid. Otherwise, you say it is invalid and there is syntax error. Okay, students? So, likewise, this Yak tool will check the syntax of the given expression. Right, so this is one of the way we execute the LEX and Yak tool. The given C program can be executed in this way, and you can see the output here. Okay, so you have LEX calc.l, then Yak cal.y. Then you are saying that you are going to compile it. That is GCC lex.yy.c y.tab.c minus w. Right, so finally you can check whether the given expression is valid or invalid. In the first case, 4 plus 5 is valid. In the second case, it is valid. In the third case, it is invalid. It is 10 plus 5 minus. In the next 10 by 5, it is valid. 2 plus 5 into 3 is valid. 2 into 4 plus is invalid because one operand is missing, right? And then 2 modulus 5, right? So here it is valid. Okay, students, like this, with the help of this LEX and YAK tool, we can easily identify the various errors in our phase 1 and phase 2 of the compiler. Right now, this is a block diagram which combines our LEX and YAK. LEX and YAK generate C code for your analyzer and parser. So you have the lexical rules. So first is your C code, then you have the LEX, right? Then you have the input char string, YLX, C code, lexical analyzer, which is otherwise called as tokenizer or scanner. Then you have the grammar rules. So we are using context-free grammar here, C code. The name of the tool is yet another compiler. Whatever tokens you get from the lexical analyzer, you give us input to the YY pass and you check whether the given syntax is right or not. Okay, finally we pass the input and we check whether it is valid or invalid. Thank you, students. I think I have made clear about the LEX and YAK tool. So we have completed the phase 1, phase 2 of the compiler, and then we have seen a case study with that of how to do the operations, right? Thank you, students.